lecture slides. So the slide number 29 is what I just discussed, right? So the matrices are written out and the solution is provided, but I also showed you how the solution is derived using these slides. Okay, so now we look at some examples. So how we use the matrix formulations in real life cases. If you have any questions, I can pause for a brief moment. Okay, so then going forward, one example is that of the thin lens. So thin lens basically means the distance traveled by the ray inside the lens can be neglected. So the propagation inside the lens, we don't need to worry about that. And in this case, we are just analyzing the lens. So we are just worried about the ray which is entering the lens from the left-hand side and the ray which is exiting the ray from the right-hand side. No propagation is taken into account over here. No propagation of the ray on the left-hand side, none on the right-hand side, and the lens is thin. So anything the ray propagates, any distance propagates inside the lens is neglected. So we write our output matrix equals, remember, going from output side to input side. So refraction at second surface is written first. So refraction at second spherical interface multiplied by refraction at first spherical interface times the input matrix. And remember, that's all we have to do. Just write out the matrix equations, then refer back to the slide for the refraction by spherical surface matrix and just plug it in here. And that's all that's done over here. So for the second spherical surface, what is the form of the equations? It's n prime minus n over r, right? So for the second spherical surface, n prime is 1 because that's the output side, minus n prime, which is whatever is the refractive index of the lens, over r, that's given radius of curvature, with a negative sign in front. And that's exactly what is here. So with a negative sign in front, 1 minus n prime over r prime. So actually, yeah, so okay, it's made more general. So the two surfaces have two different radii of curvature. So r prime on the right and r on the left hand side. So r prime. For the second matrix, we have to look at the first spherical interface. So n prime minus 1 over r with the negative sign in front. And everything else is 1, 0, 1, 1, 0. So you do one matrix multiplication in this case, and you derive this final system matrix for the thin lens. Right? Very easy to see since all the other terms are 1, 0, 1. So everything is 1, 0, 1, and you have just one term which is a little bit complicated, right? Over here. So very important to keep in mind this term, the M12 term with a negative sign in front of it is called the power of the thin lens. And why is this important? Because this is exactly, this term contains all the information that is required to manufacture this lens. So suppose someone asks for a prescription of some eyeglasses and says, okay, I need a lens with such certain power like this. All you need to remember, all you need to know to physically design that lens and manufacture it are the radii of curvature of the two sides, r and r prime, and the material out of which the lens is going to be made, which is n prime. So you have to pick a certain material like glass of some certain type of glass. So it would have small changes in refractive index. And that's all that is in this term. Look, n prime, r and r prime. So this equation is also called the lens maker's formula. So if you simplify this equation, it's n prime minus 1, you take outside, and then you have 1 over r minus 1 over r prime. So the power of the thin lens is the negative of the M1. Yeah.
Yeah, for the radius of curvature at the backward thing, for the second surface, r prime should be considered at -1.
Yes, that's true. Yeah. So yeah, that's actually what I was going to say next. So also remember for the sign convention,
Yes.
Yeah. So when you plug in the final values, that's where you take care of the sign. So yeah, very good question.
Okay, thank you.
Yeah. So few things we have to keep in mind when solving these problems, other than this slide, is basically this slide, sign conventions. So these slides, number 24, number 28, very important to keep in mind. So basically a combination of these two slides should give you the correct answer to the problem. Right? So in this case, I've just written the general form. So this can also be, could have been curved the other way. I mean, this could, so this looks convex. It could have been curved like a concave surface. So then you would have to use a different sign for that, whatever is there in the sign conventions. Right? So yeah. Okay, so power of the surfaces, positive power bends rays inwards. So if you have a plano convex lens, which means one surface is straight surface, plane surface, and the other surface is curved, plano convex lens, the rays traveling parallel to the optical axis will bend inward. Biconvex lens, same thing. Negative power means the rays traveling parallel to the optical axis will bend outward. So this is plano convex lens, plane one side. Sorry, plano concave lens, so concave on the other side. Biconcave lens, two sides are concave, and so on. Just some definitions, nothing much for me to discuss in this case. So yeah, so one interesting thing is, so parallel rays traveling parallel to the optical axis means plane wavefronts, and they are getting bent towards the optical axis means they are being brought to a focus, which means the wavefronts become converging. And in this case, they are bending outward, means the wavefronts become diverging. Okay. So remember, this case is the animation that I showed previously. Okay. Again, a slide which just summarizes important things. So from the matrix formulation, in the final system matrix, the power is the negative M12 term. And the focal length, by the way, is defined as 1 over power. Okay. Yeah, so, oh, okay. One interesting thing to note is this is the power, right? So what is the unit of the power? So we can see refractive index has no unit, it's unitless. And R is radius of curvature, so that would have the unit of length. So, and that's in the denominator. So the power of the thin lens would have an unit of 1 over length, otherwise known as diopters. Whereas the focal length, being the inverse of the power, would obviously have the units of length, meters.
Right? I have a question. I'm sorry.
Yeah, no, go ahead.
Oh, so can you come back on that slide one more, please? Yeah, that one. So I'm trying, this is a thin lens. I'm trying to understand, on my view, like R and R prime should be very close, right? They're almost the same value, right?
Yeah, because it's the thin lens, they don't need to necessarily be the same, but all the main take-home approximation in the case of a thin lens is that the distance the light ray propagates inside the lens is neglected. So obviously we'll see that in real life cases, we don't usually work with thin lenses, and there would be a certain distance that the ray would have to travel inside the lens, and we would have to take that into account. But this is like a special case of a general lens. A general lens would have refraction at the left-hand surface, then some propagation inside the lens, and then refraction at the right-hand surface. But in this case, if you make a special case where the lens, you just squeeze down the center of the lens so that there is no propagation, this is the case. Let's just say. So it doesn't necessarily need to be, but yes, you're right that they have to be very close to each other. But this is the general form, let's say. Obviously, if these, yeah.
Okay. Understood. Thank you very much.
Yeah. Okay, so this is the, so next we go on to a couple of more definitions. So more a bunch of slides next are just definitions. So thick lens, this is actually, so what you asked, this is the more realistic case. So a thick lens, which means two curved surfaces with some distance that the ray has to travel inside the lens. You can also think of this as a complicated multiple lens system, suppose inside. So there would be many places where the ray would refract and then travel some distance and refract. In the case of a thick lens, there is just one lens here. But if this is complicated, so we have to take into account, like, where do we, if we treat this as a black box, right? And where do we treat, what planes do we look at for the final refractions and so on? So we define some certain points and planes with respect to the complex lens system, which is the second focal plane, the first focal plane. So second focal plane means basically if you have parallel rays going in, the point at which all the rays come to a focus on the optical axis is defined as the second focal plane. The first focal plane is if you have a point source on the optical axis, the distance of the point source that it has to be placed away from the first surface so that the output rays become parallel is called the first focal plane. And the second principal plane is like an equivalent plane, which we can mathematically deduce as a plane from which the refraction can be considered to be the last refraction from the optical system, which bends all the rays to one point. So obviously, if this is a complicated 4 or 5 lens systems, there isn't one plane from which it just refracts and then goes out. There's going to be many refractions, then some propagation, refraction, propagation, refraction. But this is an equivalent version of the system so that we can analyze it in a simple manner. So just remember some definitions. Second principal plane is the last plane from which the parallel rays are assumed to refract toward the optical axis. First principal plane is the opposite. Basically, these are just reversed and so on. And using those equations, we can define some focal lengths. So the front focal length is the distance of the first focal plane from the first surface. But you can see, since this is a thick lens, there is some more distance that you have to travel to reach the first principal plane. So if you add that distance, this entire distance is called the effective focal length. The same for the back focal plane. From the interface to the second focal plane is the back focal plane, and if you add the thickness or the distance, extra distance, is called effective focal. Okay. And the significance, yeah, like I said, the significance of principal planes is if you have a complex optical system, you cannot talk about all these different planes at which refraction happen and so on. So the second principal plane, you can treat it as whatever be the refraction inside. This is the last plane from which the rays will bend toward the optical axis. And the reverse is true for the first principal plane. These are just some definitions that we should keep in mind, not terribly important for this class or problems that we would be solving here. Okay, one more sort of a more realistic example of the thick lens. So basically, this is the more general form. You have two surfaces with certain distance in between them. So the ray travels from left to right. It hits the first curved surface, travels a certain distance inside the lens, then refracts out from the interface between the lens and the outside material. So the thin lens case was basically just shrinking down D1 to a negligible value. So same as last time, these two, you go from output to input. So you write your output matrix equals your refraction at second surface matrix is written first. Then propagation inside the lens is written here. And then refraction at first surface is written over here, right? Just refer to the slides. Same, translation through uniform medium, refraction by spherical surface, just bring them down over here and substitute them. So imagine this would have taken you much longer to solve by doing geometry and stuff like that. So everything else, just tally all the whatever n1, the output is n prime, and so on. You could have added some free space propagation outside, but that doesn't really matter for analyzing just the lens. So we are just considering the fact where the lens is entering, the ray is entering the lens and the ray is exiting the lens. So refraction, propagation, refraction, written in the matrix form as refraction from the second surface, propagation, then refraction from the first. So you do the matrix multiplication, and maybe you can do this as a homework. I'll also try to maybe do this and add to the slides, like do all the multiplications so that you get some practice. So again, I usually do the second matrix, multiply this last two matrices first, and then I multiply the first one with that, and so on. So you get this entire large matrix. And here we see that, remember, the power term for the lens, the thin lens power term, was negative of M12 term. So this is the thick lens power term, right? So here. And this is the thick lens power term, negative of M12. And remember, focal length was inverse of power. And we just defined in the case of thick lenses, the effective focal length, right? The distance of the surface to the principal plane added to the back or front focal length. So the power can now, we can also define the effective focal length f as 1 over as f, and 1 over f, the power, is this term. So this is the power term here. Power equals 1 over focal length here. And in the case of a thick lens system, the focal length is the effective focal length, as shown here. Okay, so that's all the significance of all these terms that we discussed, right? Effective focal length. For the thin lens, it's just focal length. For thick lens, it's effective focal length, which equals f. 1 over f equals power. Power is negative of M12 term, which is given over here. Okay. So other than the geometry, other than the matrix, all the math and all that, we have also understood, I hope, what the physical significances are of all these terms, right? Math is good, okay, it's, yeah, you have to solve the math, but it's more important that you understand what is going on. We'll be doing a software tutorial for, I think, 2 softwares in this class. And there you won't have to solve all the math, right? You will just have to define. It's a lot of fun. You just define all these lenses and so on, and then see how the rays bend and form images and so on. But it's very important to understand what is going on. What's the physics, right? It's all about these materials bending light. That's all. So some propagation of light and then some bending of light. That's it. And where it's bending from, how much distance is propagating, that's all the math is calculated. So if you can get the math correct, you'll figure out how your system works. But only physics which is involved is materials bending light. That's how lenses work, changing the direction in which the rays are traveling. That's all. Okay. So finally, we come to something important called the imaging condition. So this is ray tracing from one object and how the image of the object is being formed by this complicated optical system. So now see, since we have defined all the principal planes and all these things, we don't even need to draw the optical system, right? I mean, it can be one lens, one thick lens, thin lens, collection of thin lenses, collection of thick lenses, whatever. All we have to remember is that there is a principal plane, which is the first principal plane. There is another principal plane called the second principal plane. The first principal plane is where the parallel rays travel through and the point source rays become parallel. And the second principal plane is where the parallel rays bend and these parallel rays travel through. That's it. So you just simply trace out the rays from each point of the object. So suppose the object is this arrow. So if I concentrate on this point, I can draw out 3 types of rays. One ray which is traveling parallel to the optical axis here. So it goes parallel. So remember, second principal plane is where parallel rays go through, bend toward the focus. So it goes parallel, then it bends towards the focus and then continues traveling in this direction. Then we can trace out another ray which basically goes in at an angle, hits the first principal plane. So what will happen? This will now become parallel to the optical axis and then bend again and go out. And the third ray, which basically goes through the focus, that is going to hit the first principal plane and then become parallel. Remember, because we defined the first principal plane as if you have a point source at the focus, the bent light rays will become parallel. So basically a light ray going through the focus becomes parallel. So now all these 3 points, you can just draw them out by hand. they will converge to a point. And that point is going to be the exact representation for an ideal system, by the way. No system is ideal, so it will never be exact. Some information is usually always lost, but it's a very good representation as much as possible of this point. So now if we do this for all the points in the object, you can reproduce that object here in the form of an image. So basically, if you have your eye here, you can see the image. If you have the camera sensor, you can record the image in the form of a photograph, video, whatever. So this is how the world of photography works. This entire region over here, which has not been drawn, would have all your lenses and everything. And this region where the image is would have your sensor. The outside world is here, and you were able to replicate the entire outside world on your sensor. So remember, one important point to notice is that the image is flipped. The object is, so this is upright, right? The arrow is pointing up. With respect to the optical axis, the image is flipped. It's pointing downward. That is the true for all optical systems, including the human eye. So the image formed by the human eye on the retina is actually upside down, and your brain takes into account all the information that it gets from other sense organs and flips it right side up, basically. And the same case for sensors. All camera sensors record images upside down, and then your software basically turns it right way up, and you can see it on the phone like that. Because this is how exactly the physics works. So that's it. So, and I think this is something we also did when we were in high school, but this is the more in-depth study of how the imaging works. So if I analyze this system, I would have propagation first, then interaction with the system, and propagation again. So that would be some complicated matrices here, but we have simplified the matrix to assume that this is a system which has a certain power, right? A collection of lenses would have a certain power. Each lens has a certain power. So if you combine lenses, there will be a final equivalent power for the optical system. So if we term that as P, we can write that as the system matrix, right? Remember, we said for an optical system, the system matrix is 1, 0, and 1 are the terms, and then negative M12 is the power. So that's all we have written. And in analyzing this, we have written the system matrix. So remember, your output matrix equals system matrix times input matrix. So system matrix equals going from output to input. So first, propagation in n prime medium. So 1, 0. The distance propagated is s prime. So s prime over n prime and 1. Then the optical system matrix written in the form of 1, 0, 1 and minus power, or the minus power term. And then 1. Again, same for this side. So 1, 0, s over n and 1. You do two multiplications. So this matrix multiplied by this, and then this multiplied by the result, and you get this term. Oops. No, what I keep clicking. What is that? I don't know. I have to fix this. Anyway, so these are the 4 terms. Why is this term important? So what we are trying to learn in this slide is the imaging condition. That is, our problem is what has to happen for this image to form, right? So this is the ideal version drawn out in the form of a geometric problem. But in real life, you need to know what these distances are. S, S prime, how are they related? With the one property of the optical system. What is that property? The power or the focal length. How are they related? And then you can properly bring your object into focus and get a proper image, right? If you didn't know this, the image would be blurred, right? If you move the object closer or further away, the rays would travel in different directions, in having different distances with respect to the optical axis, and they wouldn't converge to a point, and your image wouldn't be sharp. So what is the imaging condition? What do we need to do to get a proper image? So we have this term, right? And what we see is, this is what the equation looks like. The output matrix equals the system matrix times the input matrix. Now we can just look from mathematics point of view. If you do the matrix multiplication, what will happen? This term will be, the first term will be this times this plus this times this, which will be equated with n this term, alpha prime term. The second term will be this term multiplied by this term plus this term multiplied by this term. So your x prime will have on the right hand side two terms. This term multiplied by n alpha and this term multiplied by x. Now to properly form an image, physically what needs to happen? All the rays which are going out from the object have to be collected to the image, irrespective of the angle in which the rays went out. So you cannot have an angle dependence on the rays, right? So x prime and x, which relate the point, this point, right? So this point is defined by its height from the optical axis, x prime, and this point is defined by its height from the optical axis, x. If this point is to be reproduced here, we have to remove all the angle dependence. So this term has to go to 0, which is the only term which was multiplied by the input angle alpha. Maybe I can actually put one extra slide at the end of the math slide which solves this problem, and maybe it will be more helpful. But basically, if you put this equals 0, this is what you get. So look, s prime over n prime plus s over n minus this equals 0 means you take the p s s prime term to the right hand side of the 0, and you basically get this, and you do some manipulation, and this is the imaging condition. Very general form of the imaging condition. This is something we learned in school. If your entire system is in air, right? Basically, if your object is in air and your image is in air, your n and n prime becomes 1, right? See? So you replace n by 1 and n prime by 1, and s is your object distance, s prime is your image distance, and p, the power, is 1 over focal length. So this is for the system immersed in air, 1 over object distance plus 1 over image distance equals 1 over focal length. For a complicated optical system, remember, this is the effective focal length. But this is something we learned many years back when we were doing basic optics in school, the imaging condition. But this is the more in-depth general understanding of how the imaging condition is derived from the point of mathematics. In school, we were told, oh, look here, this is how it works. If you place an object here, you get an image here with a lens with a certain focal length. This is how they're related. But now we understand from better mathematics point of view how exactly the relationship works, how we were able to get to this point. So this is the imaging condition. A couple of things before I end for today. When the imaging condition is satisfied, that is when this is true, which means a proper image is formed, sharp, good-looking image is formed. The magnification is basically your height of the image over the height of the object, which is equal to this term, which is the first term in this equation. The angular magnification, which is the angle of the image subtended with respect to the optical system to that of the object, is this term. And this here is a generalized summary of any optical system. Your image, now we can call the output as an image. The image equals a system matrix times the object, which was the input. So if you have a system matrix like that, the power of the system is given by negative of the M12 term over here. The imaging condition is setting this term to 0. The lateral magnification is this term, and the angular magnification is this term. So suppose you're given a problem to solve, like, okay, this is the situation, this is an optical system. What is the imaging condition? So you basically write out your matrices, multiply them, get the final matrix, then set the M21 term to 0 and say, this is the imaging condition. What is the power of the optical system? You set this term to minus of this term, that's the power of the optical system, and so on. So this is basically how you use the matrix formulations to solve. I think it's about time, so I'll just stop. A few more slides. Maybe I can borrow some time from future lectures to go over. Okay. So Dr. Menon, it's over to you. Still around?
Okay. Yeah. Sorry, a little loud here, but let me take it back. Let's see. I think, okay, at this point, I think we can end. And what my suggestion is make sure